Hello, and welcome back to CS 500 Design and Analysis of Algorithms. We're in chapter 2 talking about tree data structures. So let me share the slides and help you recall. Last time we talked about abstract data types, how to hide hardware and implementation details in order to realize mathematical data types and such as integers. We recalled basic data types and derived data types such as linked data types, including trees, binary trees. And then we ended recalling AVL trees. AVL trees are binary trees which have some nice properties. Namely, they provide a nice trade-off between, on the one hand, having small height, and on the other hand, having small cost for maintaining this property. So for example, perfectly balanced binary trees maintain minimal height, but they are costly to maintain. On the other hand, general binary trees are easy to maintain, but they have possibly degenerate height, which can be at most linear. So our goal is to have still minimal height, but only up to a constant factor. And this relaxation turns out to allow for efficient maintenance when considering AVL trees. So we recall the definition of AVL trees and some quantitative properties, namely on the relation between height and the number of nodes in such an AVL tree. And so today we're going to recall that, and we will consider operations on AVL trees such as insertion and deletion. We will analyze the cost of these operations, and we will end with a deficiency or defect of AVL trees, namely they are not very efficient for merging. So these are topics that have already been covered, for example, in CS 300, Introduction to Algorithms. But today we move on further, and we will going to discuss also binomial trees and binomial heaps, also known as binomial forest. We'll recall the definition of binomial trees and binomial heaps, operations supported on binomial trees and binomial heaps. We will analyze the cost of these operations. Specifically, the operations we consider will be extract min operation, decrease key operation, and newly the merge operation, which is new and supported now efficiently as opposed to AVL trees. So that's our plan for today. So let's start by recalling AVL trees and their definition. So one important thing about the definition of AVL trees is that it is a local property. Namely, in an AVL tree, for every node, root node, but also for internal nodes, the two sibling subtrees must have height difference at most 1. So here you see some example of such AVL trees, where for each node, for the root node, the two subtrees have height difference at most 1, but also for every internal node, the subtrees have height difference at most 1. So this is a local property, whereas for perfectly balanced binary trees, perfect balance is a global property. And local properties generally are easier to maintain. And that's what we're going to see here. But first observe that these example AVL trees are actually minimal AVL trees. So this is an example AVL tree of height 0, one of height 1, height 2, height 3, height 4. And they're actually minimal in the sense that no smaller AVL tree of height 3 can exist. No AVL tree of height 3 with less nodes. If we remove any node here, either that will result in a violation of the AVL property, or it will result in an AVL tree of less height less than 3. So these are AVL trees of given height that have the fewest possible number of nodes. Or put differently, these are the tallest or the deepest AVL trees of a given number of nodes. So that's why we're going to analyze these, the tallest AVL trees, and therefore any other AVL tree will be at most that tall, will be at most that deep, and thus will have a bound on the depth or the height of any other AVL tree. So let's analyze the minimal number of nodes of an AVL tree of height h, that is the size of these minimal AVL trees depending on the height parameter. And we're going to analyze that, and it turns out that this analysis is similar to the analysis of Fibonacci numbers. So let me first start with an induction start for Fibonacci numbers, and actually we're starting to start with the first Fibonacci number, which you recall has value 2, and we observe that this is the minimal number of nodes of an AVL tree of height 0 plus 1, which is kind of trivial because an AVL tree of height 0, this is just this single AVL tree, and if we add 1, that gives 2, and this is exactly F2, if you recall the definition of Fibonacci numbers. Then we look at the induction step. How do we construct a minimal AVL tree of height h plus 1? By taking an AVL tree of height h and taking an AVL tree of height h minus 1 and combining, concatenating them by adding one common new root. This is how these trees have been obtained. So here we take an AVL tree of height 3. Here we take an AVL tree of height 2. Here are these AVL trees. And we combine them into an AVL tree of height 4 by joining them under one new common root, right? So here's here the new common root. Right. And that increases the height because now we had added this new root, and the two previous AVL trees are moved down by one level. So that's why the height is increased to 1. And this is this is the smallest possible AVL tree of height h plus 1 we can get. Now we want to analyze this recurrence, right? And as I said, well, this is it looks like a new recurrence, but now let's just for mathematical purposes add 1 on both sides of this equation. So then it's still true, right? Adding 1 on both sides makes this still true. But now this quantity that we're analyzing at the recurrence n of h plus 1 is the very same recurrence as of Fibonacci numbers, right? So here, replace this whole expression, including the plus 1, with fh. Replace this expression, including the plus 1, with fh minus 1. And here we have h plus 1 plus 1. So this is the very same recurrence, and therefore it has the same solution, right? Only the start is different, kind of a shift. Here we have n of 0. Here we have f3. So adding 3 to the index and adding 1 to the value. Inside adding 3, outside adding 1. That's the result. So this is thus equal to fh plus 4. And now recall that we do have an explicit solution for Fibonacci numbers, namely Binot's formula, and we thus now also know the asymptotic growth of Fibonacci numbers, which is exponential, with the base being the golden mean. So by therefore also the minimal number of nodes of AVL tree of height h grows exponentially, there's only two shifts, one in the argument plus 3, right? Here h plus 1, here h plus 4. So h plus n, so the Fibonacci number index h plus 3, but this gives only a constant factor difference here. And also there's a shift in the value plus 1, but that's also just a constant difference. So as asymptotically, that means also n of h grows exponentially. And now solving that equation, n of h being exponential in h, taking the logarithm of both sides results in h being logarithmic in n, and therefore that means that AVL trees indeed have height at most logarithmic, which is what we were hoping for. So optimally perfectly balanced trees have height equal to the logarithm, and here we allow for constant factor relaxation, and still we have up to this constant factor, we still have optimal height. So that's analysis recalled from last time. And let's now move on to recall also operations on AVL tree, and in particular how to maintain this local property of being almost balanced up to height difference at most 1. And in order to reflect that, we're going to add indicators. And we were going to store, in addition to the content of each node, in addition to the key value in each node, we're also going to store in each node balance indicator plus, 0, and minus. That is to reflect whether the left and right subtrees of that node either have equal height difference, which is reflected with indicator 0, or whether the left subtree is deeper, has height plus 1, or the right subtree is deeper, has height plus 1. So these are the only possible cases according to the very definition of AVL tree. So height difference 2, for example, is prohibited. Therefore, we will not have, or we will not allow a balance indicator like plus plus, which would mean that the height difference is 2, or minus minus, which would also indicate that the height difference is 2. Now, we know the usual operations on binary search tree, how to insert an element. First, we're going to search where to insert the element, and then we create and add a new leaf at that position. We also know how to delete an element in a regular binary tree, and then we would simply delete that node and then append the subtree of that node as an additional subtree to that parent. And when we do the same now for AVL tree, these two operations could lead to a violation of the AVL property, but using the indicators, we will be able, or our implementation, our algorithm will be able to detect that violation. So let me give you some examples. Here's an example, AVL tree, and in this example, the left and right subtree have the same height. So that means in the root stores balance indicator 0. And also 0 is stored in the both subtrees because they are leaves. They don't have any successors. So trivially, left and right subtree of this leaf have the same height, they're absent. And now let's suppose that we insert a new element at the left. Okay, so we insert this new element, and the key value is not indicated here, but in the example, it's supposed that the element has key value smaller than this root. So we'll proceed to the left, and has key value smaller than this node. So it will continue to proceed to the left, and then it will be inserted here as a new leaf. But this new leaf now changes the balance in the tree. And it changes the balance in two parts. First, it changes the balance of this node, which used to be a leaf. So we're going to update that to minus. But then also it changes the balance of the root, which used to be perfectly balanced, but it also receives the new indicator minus. And what is the general rule for these updates? How do we process them algorithmically, locally? The way to do that is, recall that we first proceed downwards in the tree to find the position where to insert the new leaf. And then that's a new part that is new in AVL trees compared to general binary search tree. Now we also proceed backwards up. Okay, so in usual binary search tree, we just walk downwards until finding the position where to add the new leaf. But now we also proceed upwards, and the rule in proceeding upwards is the following. Whenever we proceed upwards, we change a zero indicator, balance indicator, into a minus because we have added a new leaf at the left. And then we proceed recursively up again. Next level, we turn a zero into a minus, and so on, moving up, back up, until we are at the root. And we do that as long as we find indicators zero. Every zero that we encounter on the way back up will be turned into a minus. How about other indicators? Well, let's consider another example. So in this example, we start with this AVL tree and observe that in this AVL tree, the root is balanced, so it's indicator zero because both subtrees have the same height. These nodes are balanced differently. No left subtree, but one right subtree. No left subtree, one right subtree. And now let's suppose that we again insert an element, but when proceeding downwards to find the position where to insert the new leaf, now we proceed, in this example, proceed to the right, and then we proceed to the left. So the new node will be inserted here. And then the new thing about AVL trees, we now proceed backwards up to update the balance indicators. And our previous rule was, when proceeding up, whenever we encounter balance indicator zero, we turn that into a minus. But here, when we proceed up, we do not encounter balance indicator zero, but we encounter balance indicator plus. And the rule now says, whenever we encounter plus, then we turn that into a zero. So this is like decrementing the balance indicator whenever we insert an element, a new leaf at the left. So here we have inserted an element, new leaf at the left. So we decrement the balance indicator, plus becomes zero, zero becomes minus. Now, what if we encounter minus? We haven't covered that case yet, right? So let's cover that case. Here again, we start with a AVL tree. Now we start with an imbalance case, minus in the root, minus here. And in our example, we insert a new leaf again to the left. These are all examples about inserting an element at the left. And the rule says, after inserting, moving back up and decrementing each balance indicator. So now we need to decrement that balance indicator zero, becomes a minus. Then moving further up, balance indicator minus becomes a double minus. And now recall that a double minus is prohibited. Double minus is indicating that the height difference is actually 2 rather than at most 1. So now we need to do some repairing, some maintenance. And the maintenance, which we'll discuss in a few minutes, will actually rebalance these three nodes to make them balance. So this node will become the new parent. This node will become the new child of that. And this will remain a child. And this, you see here, restores the balance. And then we have avoided the double minus. It has become here the 0. And once we have thus rebalanced, we can stop moving upwards and rebalancing because this balance indicator has already been taken care of. So this is a first example of how to insert an element at the left. The case of inserting an element at the right is perfectly dual to that. Only when inserting an element to the right, we will not decrement the balance indicator, but we will increment it. So we will turn a 0 into a plus, and we will return a minus into a 0, and we will turn a plus into a double plus, which is a violation. So we will need to rebalance with a double plus, but this is the same case, just a mirror symmetry, right? So left and right are perfectly mirror symmetric, and therefore will only suffices to discuss here one case only, one side only. And this is what we're going to do now, namely the rebalancing operation. Rebalancing operation can be performed in two directions. So the case we've been discussing here is when there's an unbalance on the left side. Unbalance on the left side means that the subtree A alpha is deeper than the subtree beta here of the node A. When you see there's already an imbalance, this subtree is deeper. The subtree at A, capital A, is deeper than the subtree gamma. So gamma denotes an entire subtree. A is deeper, but it's still within the bound of 1. But now let's suppose that we've inserted a new element at the leaf to this subtree alpha, then the balance becomes too much, and we need to rebalance. And rebalancing means proceeding here from right to this left picture. And that means we kind of move the former root B downwards and instead upgrade the node A to become the new node. So this is called a rotation. It's a right rotation because we move B down and A up. So this is kind of a clockwise rotation from here to here. And after this rotation, what used to be the deeper tree alpha has been moved up, whereas the more shallow tree gamma has been moved down. So after this rotation, alpha is still deeper, but after it has been moved up, it is not exceeding the depth of gamma, which has been moved down. So after this right rotation from here to here, the balance has been restored. That's one direction, and the opposite direction is simply perform the rotation in the other way. Here, suppose that gamma is deeper than alpha. We may have inserted a new leaf at gamma, and thus have violated the balance property. The indicator at node A may have become a double plus. And then we perform a left rotation, a counterclockwise rotation, to obtain this situation. And in this situation, the formerly deeper tree gamma has been moved up, and the formerly more shallow tree alpha has been moved down. And thus we can change the balance indicator back from double plus here to a 0 here and to a 0 here. And this is what you see has happened from here to here. Here, this became a double minus, which was this situation, and we've moved to this situation by performing a clockwise rotation, lifting this node up, moving this node down, and then everything is balanced again, zeros. And this is a local operation because it doesn't affect the higher part. So let me show you this rotation operation, two complementary right rotation or left rotation, which are complement to each other with an animation. You see what's happening here. And you also see here that this only involves changing pointers, right? pointers between subtrees or roots of subtrees and internal nodes. And changing pointer, this is what makes these data structures so efficient. Changing a pointer has constant cost. So one pointer has constant cost. So we don't need to really move large chunks of data, large chunks of memory as we would have to do when we were operating on arrays. Recall that inserting and deleting elements in an array is very costly because we have to move entirely chunks of data up and down. But here the rotation operation of moving these subtrees is not really moving data, but it's only moving pointers. Okay, so here you see the left and right rotation. And but there's one case that I haven't covered yet, or actually two cases. Namely, in some cases, we will need to do two rotations. So this was one rotation, left rotation or right rotation, but we might also sometimes need to do two rotations. And this is the case when the subtree that is the cause for the imbalance is actually the middle subtree, beta. Right? So we've discussed the case where gamma is the source of the balance violation, and the case where alpha is the source of the balance violation. This is the rightmost subtree, this is the leftmost subtree, but we haven't talked about the case where the middle subtree beta is the source of the violation. And in that case, we perform two rotations as indicated here. So this is a case where the middle subtree is the source of the imbalance, which you see here. So this is a leftmost subtree, no problem here. This is a rightmost subtree, no problem here. But here, this is the middle subtree, and this is where which causes the balance violation. So what do we do here? Well, we perform two rotations. First, we move that violating subtree up to become the new root, the new parent, and we move this down. But then we still have a violation, but this is a violation we've already discussed before, where the violation is caused by a leftmost subtree. So here we know we also only do one further rotation, and then we have restored balance. So this is typical mathematical thinking, right? We first discuss how to restore balance, and when we encounter a case where this is not applicable, then we perform one rotation, and then we are back in the situation we've already discussed, where we perform another rotation. So that means two rotations. So yes, the same applies to, so this is the case here where this beta is causing the imbalancing. And similarly, when we're in this situation and this beta is causing the imbalance, then again we perform two rotations in the mirror symmetric way to restore balance. So this is what you see here. But just to be clear, even two rotations have only constant cost, because in each rotation, a constant number of pointer gets changed, and when two rotations, still a constant number of pointers get changed. So this is constant cost. So this concludes our discussion of the rebalancing operation, and we already had discussed how to update the balance indicators accordingly while moving up. Whenever we don't need to update an internal node balance indicator, then we also stop proceeding upwards, back upwards. So this moving down and moving back upwards only proceeds as we need to update balance indicators. So let's now see the cost. What is the cost? Well, moving down, as we saw, has cost proportional to the height, which for our analysis shows to be at most logarithmic n of n. Then proceeding backwards up to update the balance indicators also has cost at most the height, right? In each step, we go one step back upwards at most height, which is still additional log n of log n. And at most once happens the case where we need to rebalance once or twice, which is constant. So overall, the cost of going down and going back upward and updating balance indicators and rebalancing is still all bounded by O of log n. Only the constant hidden here in the O of log n becomes larger, but it's just a constant. And as you recall, we're only interested in asymptotic growth and look at optimizing constant factors only later. According to Donald Knuth, premature optimization is the root of all evil. So that concludes our discussion, or rather reminder of AVL tree from CS 300. And now, right, yes. And this is the symmetric case, right? The mirror symmetric case. And we've seen that the search cost for searching where to insert a new element is at most logarithmic, namely at most the height. Same for inserting, which is kind of the what we discussed here. Namely, insertion means first searching where to insert the new element as a new leaf, and then proceeding backwards, upwards, which is again at most logarithmic cost. And I haven't discussed the case of deleting, because deleting is simply kind of the dual to insertion. So the same as before, namely first search the node which is to be deleted, then delete it, which involves juggling with the two subtrees that were attached to that node, and possibly performing updating the balance indicators and performing possibly some rebalancing rotations as indicated here. So that looks all very promising, right? All the operations now have logarithmic cost, which is very fast. As you recall, our slowest computer was still faster than the fastest computer when the slowest computer is running a log time algorithm and the fastest computer is running an inefficient asymptotic algorithm. But as I said, AVL trees have one deficiency, namely that's the merge operation. Namely, AVL trees can be merged in linear time only. Now, how can we merge AVL trees in linear time? That's maybe we'll post that as homework, but let me remind you of a trivial way of merging two AVL trees, which has cost n log n, so logarithmic factor slower than the claimed linear running time here. Namely, take one AVL tree, maybe the larger one, and then repeatedly delete elements from the other AVL tree and repeatedly call insert in the first AVL tree. Let me say that again. A trivial algorithm for merging two AVL trees is fix the one AVL tree and the other AVL tree repeatedly delete a node, which has cost log n, and then repeatedly insert that node into the other AVL tree, which has cost log n as well. And we repeat that n times. So in this way, we can merge two AVL trees with overall cost n log n. Now, n log n, one can actually improve that to result in merging two AVL trees with linear cost O of n, which is something I won't discuss here. Maybe this will be an assignment, so you might want to look into it, because our goal here is now to proceed to a different data structure, which supports merge operation in logarithmic time. AVL trees cannot do that. So that's what we're going to do now. And these new data structure are called binomial heaps or binomial forest. And as the name suggests, a binomial forest is a collection of binomial trees. So let's recall what is a binomial tree. A binomial tree is an ordered tree which is defined recursively with the following property. So I'm going to recall what is an ordered tree. An ordered tree has the property that for every node, the elements in the left subtree are smaller and the elements in the right subtree are larger. This is helpful for us in order to be able to search. Well, that's a search tree. But here we're talking about ordered trees, which are slightly different. Namely, in an ordered tree, the smallest key must be in the root. So this is something different from a search tree. In a search tree, the elements to the left are smaller than the elements to the right. In an ordered tree, the element in the root is smaller than the elements in both of its subtrees. So, but let's first talk about the height of a binomial tree. So here you see in induction start, the height, a binomial tree of height 0 is just one node. And inductively, a binomial tree of height k consists of a binomial tree of height k minus 1 and one of height k minus 1 being attached to each other, one of them being the parent and the other being the child. Okay? So spelling out that recursion, we come at the following examples. This is the trivial binomial tree of height 0 we discussed here. Binomial tree of height 1, recall, binomial tree of height 1 is a binomial tree of height 0 and another binomial tree of height 0 attached to it. So this is what you see here, binomial tree of height 0 and another binomial tree of height 0 attached to it. Binomial tree of height 2 is a binomial tree of height 1, this one, and another binomial tree of height 1 attached to it. Binomial tree of height 3 is a binomial tree of height 2, and another binomial tree of height 2 attached to it. These are binomial tree of height 2s combined. And so on. We take two binomial trees of height 3, combine them, making one the parent and the other the child. And this is a binomial tree of height 4. And one thing to observe or point out is that these are not binary trees, right? You see the degree of the root is growing beyond 2. And the degree of the internal nodes may also grow. So another way of looking at a binomial tree is like this. Binomial tree of height k is one root to which attached are a sequence of binomial trees. Several binomial trees because it's not binary tree. Not just two, but several of them. Namely one of height k minus 1, one of height k minus 2, one of height 2, one of height 1, one of height 0. So this is another way of looking at the binomial tree. Again, this is kind of a inductive definition. This is kind of a simple induction. Height k defined by two binomial trees of height k minus 1. And this is a mathematical induction where we use all binomial trees of height 0, 1, 2, and so on up to k minus 1 to define binomial tree of height k. Right? Recall these two ways of induction from discrete mathematics. Okay. So, and you see that these actually are the same definition, right? And we will look at them in both ways when we perform the analysis of properties. So let's collect some properties of binomial trees. The first property, binomial tree of height k. How many nodes does it have? It has 2 to the k nodes, and it has height k. Right? You can verify that empirically by counting, right? These 2 nodes, 4 nodes, 8 nodes, 60 nodes, and maybe we'll pose as a homework problem or as a quiz to prove that formally by induction. Using that induction maybe or that induction. And also prove by induction that a binomial tree of height k indeed has height k, thus justifying that I've been calling it a binomial tree of height k all the time. So please look into it. We will maybe post that as a homework assignment or as a quiz. Also observe we have the following degree bound. The degree of a binomial tree of height k is at most k, namely that's the degree of the node, of the root, right? So binomial tree of height 4 has, the root has degree 4, or here it's even more apparent, the root has k subtrees, therefore it has degree equal to k. Good. Also we record that on lower levels below the root, they are precisely k over d binomial coefficient many nodes, right? So here 1, 3, 3, 1. You recall these are the entries in Pascal's triangle on the 3rd row. On the 4th row, 1, 4, 6, 4, 1. And in general, these are the number of nodes on different levels at depth d, binomial tree. And now that also makes sense because recall if we add all entries on Pascal's triangle on one row, on one row, the result is 2 to the k, right? And that's true here. If we add this, and this, and this, and this, and this, then the result must be the total number of nodes, which we saw here is 2 to the k. That's the same as k over 0 plus k over 1 plus k over 2 and so on, plus k over k. So that makes sense, but yeah, you might want to practice proving that by induction formally, because it could be, have I mentioned that it could become a quiz problem? Okay, good. So these are the quantitative properties of binomial tree, but then I also mentioned the property of being an ordered tree, which is subtly different from being a search tree. Search tree has all elements left of the node smaller and all elements right of the node larger, whereas here ordered means heap ordered, which means that the node, the root has a key value smaller than all of its children. So this is the defining property. So that means this must be the smallest entry here, and all largest entries must be stored here. Not left, not right, but smallest is on top. Okay, good. So these are properties and definition of binomial trees. And our goal is to analyze the cost of maintaining that property. Maybe, later we will discuss insert and delete operation, and that will involve maintaining the heap order property. And but so far we don't even have an insert and delete operation. One major obstacle is that binomial trees can only have number of nodes which is an exponential. So for example, we cannot insert one node to this third binomial tree because then the number of nodes, so this one has 8 nodes, inserting a node will result in 9 nodes, but there exists no binomial tree of 9 nodes. The next larger binomial tree must have 16 nodes. And conversely, deleting any node from this binomial tree with 16 nodes results in a binomial tree with 15 nodes, and there exists no binomial tree with 15 nodes. The next smaller binomial tree must have 8 nodes. So we cannot insert or delete here. This is where we're going to consider binomial heaps on the next slide. But what we can do with binomial trees and will do with binomial trees, merging two of them. Namely, taking two binomial trees of same height k and combining them into one binomial tree of height k plus 1 as indicated here. And in order to do that, remember we need to choose one of them to become the new parent and the other one to become the new child, which is how to break ties, right? They look all the same. And this is where the order or heap order comes into account. Namely, when we're merging two binomial trees, or both of height k, we look at their root key value. And the one with the smaller key value will and must become the new parent. And the one with the larger key value will and must become the new child in order to maintain this. And yeah, what is the algorithmic cost of this merge operation? Well, it's constant, right? We only look at the two roots, the key values, determine which one is smaller, and then create one additional pointer, or maybe two-directional pointer, to combine them, which is all constant cost. So to summarize, and I'd like you to keep this in mind for the next slide, is that we have only one operation here, and that's a merge operation, and that has constant cost. We will also sometimes consider split operation, which cuts off one of these, which also has constant cost. We will also consider kind of a purge operation, where we take binomial tree, this one, right? The same as here, the only different view, and we cut off the root, resulting in an entire family of orphans, right? So when removing the parent from a family, the result will be a collection of orphans, and same here, only now the orphans are in turn a family of binomial trees. And here's a picture to illustrate that. So here you see a family with a parent and children of various sizes. And when cutting off the parent, there will be orphaned children. Okay, joke aside, let's move on to binomial heaps, because as I kept emphasizing, binomial trees have severe restriction. One of them, that they only occur in specific sizes. There is no binomial tree of 15 elements or of 9 elements. So what is a binomial heap, which we'll use synonymously with binomial forest? A binomial heap is simply a collection of binomial trees. And the important condition here is that in a binomial heap, every binomial tree can occur at most once. Let me say that again. Any binomial tree of a given height can occur at most once, not twice, but possibly we can omit some binomial trees of given size. So here you see the formal definition. A binomial heap is a list. Yeah, remember we talked about list data structures. Actually, it's an ascending list of binomial trees of different sizes. That's an important property. The sizes of the binomial trees in a binomial heap must all be different, must be ascending, must be strictly ascending. Therefore, each one can occur at most once, but some may actually be absent. Let's look at an example, shall we? So here you see 3 binomial trees, right? One of height 0, one of height 2, and one of height 3. So good. And now we're going to concatenate them, connect them, turn them into a list, an ascending list. First the one of height 0, then the one of height 2, and then the one of height 3. So that's the list. And observe also that these binomial trees are actually heap ordered, right? So here's the smallest element from all of this tree. Here's the smallest element from all of this. And this is the smallest element recursively of all of this. This is the smallest element of these. So these are already heap ordered. And now we put them into a list together, that is pointers from one root to the other, roots of binomial trees of increasing height. Okay, and now you see that binomial heap can occur in sizes different from exponentials, right? Different from n to the k, for example. Here's one of size 4, here's one of size 8, and here's one of size 1. So 4 plus 8 plus 1, that's 13. This is a binomial heap of 13 elements. Okay, so now we finally removed that restriction, and now we can store an arbitrary number of elements in binomial heaps. Elements which are then stored in heap order. And what would we want is to have at most logarithmic cost for all operations, right? And to this end, we need to make sure that all the depths are at most logarithmic, that all degrees of nodes are at most logarithmic, and we also make sure that the list connecting these binomial trees has at most logarithmic number of nodes, logarithmic number of elements. And let's verify that this is really the case, right? First, about the depth of each tree, we recall that every tree has an exponential number of nodes, and therefore, conversely, the depth of each tree, which is k, is exactly the logarithm of its number of nodes. So not just asymptotically, but exactly for every single tree in a binomial heap. Also recall that we we made sure that all vertices, all roots, have at most logarithmic degree, right? Yeah, because the degree, recall, is the same as the height in every binomial tree. We say that again, in a binomial tree, in every binomial tree, the root has the largest degree, and that degree is equal to the depth of the binomial tree, which we just verify to be logarithmic. And finally, how about the length of the list? To this end observes a similarity, namely, what I want to point out is a similarity of a binomial heap with representing a number in binary, right? So if we want to represent a number n in binary, then we have different value system, right? So the least significant bit has weight 1, the next significant bit has weight 2, the next one has weight 4, the next one has weight 8, and so on. And in that way, we already know that the binary length of a number has at most logarithmic length logarithmic in the value of that integer, right? So let me say that again. Representing an integer in binary will have binary length logarithmic in the value of the integer. And here we have a similar situation. Namely, here we represent the number 13 kind of in binary. How do we represent number 13 in binary? Well, 13 in binary is 1 times 8 plus 1 times 4 plus 1 times 1. 1, 1, 0, 1. 1, 1, 0, 1. Where is the O? The O comes because we don't have any binomial tree of height 1 here. One of height 3, one of height 2, none of height 1, and 1 of height 0. So that corresponds to binary representation 1, 1, 0, 1, which is 13. So put differently, when we have an arbitrary number n of nodes and we want to store them in a binomial heap, then there's only basically one way of doing that. Namely, represent that number in binary, and whenever the binary expansion of that number has a digit 1, add a binomial tree of that magnitude, of that height, and whenever the binary expansion has value 0 at that position, omit the binomial tree of that height, and this collection of binomial trees into a binomial heap will then have the required number of nodes. How many binomial trees? Well, at most as many binomial trees in the heap as there are digits 1 in the binary expansion, which we just saw. The binary expansion has length at most log n, and therefore there will be at most log n different binomial trees in a binomial heap. So yes, that's the basics of binomial heap, definition, and analysis of quantitative properties. And the most important is that all properties here are at most logarithmic. The number of binomial trees in a binomial heap, the depth of every binomial tree in such a binomial heap is at most logarithmic. The degree of every vertex in such a binomial tree is at most logarithmic. So that gives us a chance to actually operate on these binomial trees and binomial heaps in logarithmic time, which is actually what we're going to do. But I still need to show you all the operations, how to implement them. So technically speaking, we'll have a linked data structure, and pointers go to the children here on each binomial tree, back to the parent, and we have the pointers to the left sibling and to the next binomial tree here. Left sibling, the next binomial tree in the binomial heap. So that's the data structure in detail. And now let's talk about operations on binomial heaps. Operations on binomial heaps, the operations we're going to consider are merging and insertion and deletion. Well, only one deletion, namely find or extract min operation. So we're not supporting general search operation. We're not supporting general delete operation. We're going to support insert operation, and we're going to support extract min, where extract min means finding the least element, the node with the least key value, and removing that in one step. Okay. So here's the collection of operations supported by binomial heap. Create operation, create a one element binomial heap, which will have constant cost. Extract min operation, which will turn out to have logarithmic cost. Merge two binomial heaps. That's a key benefit of binomial heap over Fibonacci heap. Insert operation, logarithmic time, decrease key operation, and delete operation. So this is the set of operations we're going to support. And since we're running out of time, I'm going to stop here and recall what we talked about so far. So we recalled AVL trees and their definition, their properties, and their operations, insert, delete, and search and rebalance operations with left rotation, right rotation, and double left, double right rotation to restore balance using the balance indicators. And we saw the deficiency of AVL trees, that they cannot be merged in logarithmic time. And now we have talked about binomial trees, their definition, their properties, and about binomial heaps, their definition and their quantitative properties. And here we already see major benefit of binomial heap is they can be merged in logarithmic time, where AVL trees would incur linear cost, or actually sometimes n log n. But I still owe you the algorithms that support these operations and that maintain the binomial heap property. And this is what we'll talk about next time. So that's all for now. I'm going to stop sharing, but as always, I will still remain online to answer your questions in the chat for a few more minutes. Thank you very much for your attention, and see you next time.